Welcome to qnawire.
Here we have the equation for the electric field that is being carried in a traveling electromagnetic wave. So we'll take apart this function and see what we can learn about it. First of all, the direction in which it is traveling is given by the argument to the sinusoidal portion, or cosinusoidal in this case. So every traveling wave has a sinusoidal variation or cosinusoidal. And there is a sign between the space and the time part. If that sign is the same, then the wave is traveling in the negative direction given by the space component. So in this case, we see we are traveling to the negative x direction. The second thing we should be able to determine, but is not given here, is the polarization of the electric field. The polarization of the electric field should be perpendicular to the direction of travel. So we don't know whether it is to the z hat direction, plus or minus, or the y hat direction. So we will take it that we do not need that information. The two parameters in front of the x and the t are very important. They give you the speed of the wave. So the speed of the wave is the time portion divided by the space portion. That is sometimes called the dispersion relation of the wave. And let us just use the numbers given just so we can verify that the units are correct. So we have 1/seconds. Radians don't matter so much. They can be canceled. And the numerator does turn out to be meters per second. And if you divide those two out, you get the speed of light. So we can tell that this is an electromagnetic wave moving through a vacuum. So that is important to tell. We can determine the magnetic field amplitude. So the electric field amplitude can be found simply by looking at how large the electric field can be at any at special times and positions. And it is the number out in front is the amplitude of the electromagnetic portion of the wave. And we see it's 375 volts per meter. The amplitude of the magnetic portion of that wave, as long as you are far enough away from your source, is simply the electric field amplitude divided by c, the speed of light. So we can readily find how large the magnetic field component is, now that we know we're moving through a vacuum. Typically, the magnetic field amplitude will be much smaller than the electric field amplitude, but it is important to realize both components are carrying the same energy per unit volume. Okay, so now for the really exciting stuff is how fast the wave is oscillating is the frequency. And that is related to the omega. Let's see, 2 pi times the frequency is equal to omega, which is sometimes called the angular frequency. And we can solve for that frequency. It's quite rapid. So there's now a couple ways we can find the wavelength But before we do that, let's talk about the period of the oscillation is the inverse of the frequency in hertz. And that is simply 1.05 times 10 to the minus 15 seconds. So that is the period of oscillation. The wavelength, usually represented with a Greek letter lambda, that wavelength can be found in one of two ways. You can take the speed of light and divide by the frequency, or you could just take the inverse of the k and multiply by 2 pi. K is sometimes called the wave number. And is related to the inverse of the wavelength. So either way will work. We'll use the C over frequency technique. And we wind up with a wavelength. I will convert it into nanometers so that we can have an easier time interpreting it. What I see is that this is a wavelength that is close to the visible spectrum, but a little bit too short. So most people can see into the violet. So the violet part of the spectrum that people can see into is usually about 380 nanometers. I cannot see wavelengths that short, but 315 is shorter than that. So we are going to put this in the near ultraviolet part of the spectrum.